The title, officially announced, was Relations Among Multiple Zeta Values. It's supposed to say 1. That foreshadows that next week there will be part 2, given by someone who is much more important than I am. So that's okay. Sorry, but much more expert than I am. That's by someone. Okay. Part 2. Someone called Zagier. And in Spanish, he would even have a title. It would be Don. So now the brackets that I have put here as a kind of disclaimer, elementary relations, pretty much. So I'm not going to have any highbrow things to say, and maybe I should also add this one for newbies. Sorry. So I'm afraid that some of you will be very bored, but I'll take that risk. So just to give you a kind of overview of interesting relations among the multiple zetas. You've seen somehow the whole thing the other way around due to timing constraints. So Francis has taken the first few courses because he's away now, and it should have been the other way around, starting with elementary relations and then put them into context. But so we started with a context and more say conceptual way to look at things, and now comes sort of the more mundane stuff. Okay, but let me try to give you an idea. So we'll see more or less a collection of formulas, and it will certainly not be really comprehensive. So chosen in an idiosyncratic way, like basic and or say important and or beautiful and or I don't know what. So the ones that I feel giving somehow the nature of the zoo. So it's a veritable zoo of relations that exists among zetas. And next time there will be proofs even. I won't give proofs today, it's more like getting to know the objects or relations. And next time you'll see more next week, what how you can actually go about and prove them. Okay, and just the convention it has to start essentially with a definition which way round one takes the summation, because there are two ways in the literature, which I'm sure you've seen by now. So let's take positive integers k1 up to kd, so greater to 0, and let's take the first one greater than 1 in order to make the following sum convergent. So it's n1 greater than n2 greater nd greater 1, okay, 1 over k1 to the n1 up to kd to the nd. So that's sort of my convention. And in the literature you have maybe roughly half of the authors will have this way, the other way around, so n1 less than n2, and then you have to just flip the order of those arguments. So, so this corresponds to these are convergent sums due to that constraint. Okay, now the important notions you've also seen. Just recall. Say again, sorry.
N1 to
Oh. Yeah, very good. So the audience, some of the people in the audience are still following. So these are the exponents, and the n's are the integers over which we sum. Yeah, for instance, for d equals 1, you should have seen the familiar Riemann Zeta function. That's one way to test it. Okay, important notions. If we take the sum of these k, j, from 1 to d, this will be called the weight of k. And there will be the d itself, so the number of arguments is called the depth. So these are important notions. There are others which are less used, something called the height. I'm not going into that now. I think that may occur next time. So it's the number of indices greater than 1, that sequence, I think. And let's take it like this. And the fact that we'll use is the following: that all known results sort of are homogeneous in weight, or can be viewed as homogeneous in weight. In the following sense, they break up into relations for fixed weight. I often abbreviate weight by WT, and that will suggest that we fix the weight from now on. Now the depth is not as well behaved as the weight, at least, and but there's still a kind of depth filtration, and so we will sort, at least for now, for the exposition, so roughly according to depth, and meaning to increasing depth. So let's start with depth 1, where everything is rather familiar. Okay. What do we know in depth 1? Famous result. If you take positive even integer, zeta of 2k can be expressed in terms of known quantities. So you take 2 pi I power 2k, multiply with Bernoulli 2k, divide by 2k, and we have to multiply by zeta of 0. Okay, so where n is the nth Bernoulli number. So this is coefficient, the nth coefficient in or coefficient of t to the n in t over e to the t minus 1. So t to the n coefficient, maybe it's better, in that power series. And zeta of 0, let's call that minus 1/2. So that's maybe a way to remember the shape of this equation. That's due to Euler, 250 years old, I think. And therefore, we know that zeta 2k is polynomial in, say, zeta 2, or more precisely even zeta 2k divided by zeta 2 to the k is a rational number. So we have a good grip. So for instance, zeta 4 is 2/5 of zeta 2 squared. So if you recall that zeta 4 was pi squared over pi to the 4 over 90, and zeta 2 pi squared over 6, then you'll recognize that this hopefully is correct. And so in that sense, all the zeta 2k's are transcendental numbers. But related to each other polynomially. So that's sort of the good side of the story, or the sort of well understood side. Now, do not know much about so the odd case, zeta 3, zeta 5, so on, and not as well known. They are conjecturally all transcendental numbers and not polynomially related. So, by contrast, the previous case, and neither related to zeta evens.
When you say polynomially related, you mean with rational coefficients?
Yes. Yeah. Obviously, you can always relate them in. Yes. 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 Okay. And sort of the typically embarrassing part of the story is we demand or we expect such a big picture, and then always have to admit that on the proven side there's little known. So nothing about transcendentality, transcendence of those numbers, but one knows there are infinitely many, at least irrational numbers among them. And that's a little while, a rather recent result, about 2000. And the only explicit case, so it's not clear which ones those are, and only explicit case being zeta of 3. which is irrational. And that's a famous result by Perry in 1978. So that's roughly what we have for depth 1. Now, I left out zeta of 1, sort of on purpose, because it behaves differently. So at 1, the Riemann zeta function, as I'm sure many of you are aware of, has a pole. So Riemann zeta function zeta of S has a pole, and in fact a simple pole with residue equal to 1 has a simple pole at S equals 1 of S. And what people often do to treat that as a variable, say capital T, I've seen in many contexts, and then compare or treat other divergent series or divergent zetas, MZVs rather, sort of in relation to that number as polynomials in T. You can somehow measure how divergent such a number is. So for instance, zeta 1111 that was 4, so that was roughly like t to the 4th, and similar. And so we will see this special role of 1 next week's talk, and keyword is regularization, of which I won't talk at all. Okay, so far we've covered the positive side. What about negative or non-positive ZVs? I already mentioned 1, and I put zeta 0 equals minus 1/2. And so after analytic continuation of the Riemann zeta function, it can make sense of the zeta 1 minus n, and in fact it's essentially the Bernoulli number divided by n, and I think number 2, and minus 1 to the n. So, okay. So here again we could write it as well, okay, since I've already introduced it, I could. And the Bernoulli numbers, just to see behavior, in case you haven't done so. So you start with 1, then here you have minus 1/2. For 2 you have 1/6. Then for 3 and all the larger odd numbers, indices, you have 0, which is good to have. And here you have 1/30, 1/42, another minus 1/30, and the particularly interesting one that I've already mentioned in the first week of this activity, and several other people, I'm sure, is minus 691 divided by 2730. And this number is an unreasonably large prime. and that often serves as a traitor for Bernoulli numbers. So it will tell you, if you find 691 in a calculation, you should stop and try to look for the Bernoullis. It should be a reflex. Well, it certainly helped me several times already, and lots of other people.
Excuse me,
Yeah?
either this zeta 1 minus n, or I don't remember, zeta 1 minus n or zeta 2k, either of this is 2n factorial or 2k factorial.
No. That's for the positive side. Right? For the negative ones.
Yes.
So for instance, zeta of 0. Okay, then let's test it maybe.
But zeta 2k and zeta 1 minus n is related with gamma factor, so either one has
Factorial.
factorial
Yes.
or 2k.
Up there. Yeah, absolutely. Yes, there's a factorial up there.
Factorial.
Factorial. Sorry. Oh. So here, in red. Here are factorials. Thank you. Very good. Well spotted. So on this side there are no factorials. Slightly easier, but here factorials are important. Yes. Okay. So zeta of 0, by this definition, now becomes indeed minus 1/2, as was shown, used upstairs. And maybe it's sort of instructive to see what zeta minus 1 is. So for n equals 2, we get on the one side zeta of minus 1, which is minus b2 over 2, right? And b2, I said, is 1 over 6.
Only the problem with the sign, because you wrote minus 1 to the n,
Yes.
and then if n equals 1,
Mm-hmm.
then it's positive, and you want zeta of 0 to be negative.
No, but b is negative.
Oh, b is negative, sorry.
3 signs.
I see, b is negative.
But then there are two different conventions for Bernoullis,
I
which
see.
is also slightly confusing. Some people use it with a plus sign here, because it's also a natural power series that you can attach, and some people use that as Bernoulli, so always it's useful to be careful. Okay, so this is minus 1 to the 1, so it is plus, as you correctly say. So this is minus 1 over 12. And here zeta of minus 1 is simply the sum n to the minus 1, which is just 1 plus 2 plus 3 plus and so on. So the sum of all the positive integers is a negative number, minus 1 over 12. So this is that's Euler. Euler knew how to deal with those. So it's you think they're completely crazy, but it sort of makes sense. So the analytic continuation. So I think a way to think of this is, well, you check zeta of minus 1 against a pole of another function, the gamma function, and sort of the ratio of those of this against the corresponding pole is somehow a negative number. That's why this appears. But it has nothing really to do with the positive integers here. Okay, so I think that's maybe enough about those numbers. And depth 1. So let's pass to depth 2. Yeah, so this is really terrible. Yeah, so positive zetas. And we'll see similar instances with double and multiple zetas when we can evaluate, and there are always factorials involved.
say plus B202 is minus 112?
Yes, B2 is minus 1 of. Oh. Where are the signs? Where are the signs? So this is B2, so it's minus, yeah, so minus 1 to the 2, power 2. I wouldn't mind that. Thank you. Yeah, if you get don't worry, some such thing will be true, but it will be negative.
2n is 4.
Because the 2 is wrong. Is it? So let's check for 0. It's minus 1/2. So when n equals 1, it should be B1, which is 1/2 already, and that should be 2. Okay.
What's x?
X equals 1. Maybe just I failed again. Okay, now hopefully with less errors. And it's still mostly Euler. He looked at the double zeta values, as they're sometimes called, especially this afternoon. So the sum, the zeta AB. I have to write it again, I think. And he gave, for instance, zeta k minus 1, 1. So when the sum, well, when the last argument is 1, the second argument is 1, then you can write it as a combination of zeta k and the sum, which factor 1/2, of all the products with weight that adds up. So product of zetas has the weight which is the sum of the weights, and so I from 2 to k minus 2. So that's a relation that Euler gave, and the summation formula, sum formula, that's often called. So take all the expressions, say R k minus R. R runs from 2 to k minus 1. So all the convergent double zetas, and this adds up to zeta k. The kind of distribution of the zeta value among the double zetas. And both of these have the special case that zeta of 2, 1 is zeta 3. So that means the sum 1 over n squared, 1 over n, where n is greater than n, is supposed to be the same as sum over 1 over n squared times 1 over n. Right? It looks a bit weird at first sight, and it's not completely obvious to prove. I mean, there are 32 different proofs in what's the I think the ball lines, something like 32 variations on Goldbach on the theme by Goldbach, so with an obvious reference to Glenn Gould. So Yeah, that's the Berg. So Glengold is called Berg, but Goldbach was involved in correspondence with Euler, who wrote him that he had some such identity, and I think that's the reason why they call it Goldbach variations. And they really try to give many different proofs of that fact, trying to highlight how to approach it. And maybe this was also one of the reasons for Euler to study those double zetas in more detail, that he found that identity. And in particular, he tried to compute the number zeta 3, and rather zeta 3 divided by pi cubed seems not to be at least a simple rational number. So he computed that up to 10 significant digits, and he realized that that doesn't seem to be a simple number. Okay. Okay, what happens? So again, odd, even are separated. They're behaving in a different way. If we take, so k is odd weight, then the number zeta r, k minus r itself is already reducible in the following sense. It can be expressed as the sum of products of zetas, of single zetas. So single meaning bit 1. So for instance, zeta 5, 2 is the product of z2, zeta 5 with a coefficient, zeta 3, zeta 4 with a coefficient, and zeta 7, zeta 0 if you want. Coefficients are 5, 2, and minus 11. So some such relations, and he gave a recipe or reduction procedure. Algorithm given by Euler already. So we've seen in odd weight and depth 2, this is less interesting, reducible. We've seen in even weight and depth 1, and this was also less interesting, better understood. There was the powers of pi involved, and a similar pattern in general. So if weight is not congruent to depth in an expression, mod 2, then sort of less interesting. And for instance, I've seen that in a paper by Harakanko-Zagier. Maybe it goes back further. I'm sure people had an idea that those were reducible, but maybe it wasn't written up as such. And so in the afternoon session, I'll focus more on the first step 2 sign and the even weight. That's where something interesting happens. Yeah?
The Euler's recipe, for us, we would say it has to do with double shuffle. I mean, it's just a consequence of double shuffle. I mean, no, it's a question. Yes.
I think so. I don't recall how you derived.
Today you would say you write double shuffle and then you have a matrix and then you find this statement.
Yeah, but I doubt that you use double shuffle explicitly for that. So would be
But today
a
we
stretch.
can do that.
I think you can.
Yeah.
Yeah, I don't know how. So,
To prove that statement.
to prove that
Yes,
statement,
yeah.
or the reducibility in the higher cases, that would sort of it follows formally. I think in that paper that what they are using is double shuffle, but I don't know how explicit that is. It's very explicit.
We could do, but we need a regularization for double shuffle.
So you use the regularization there in order to deduce it.
Yeah.
So the parity statement is maybe not true if you don't use the full regularization. That's what you're saying?
I mean, to get the algorithm more explicit to this question, if
Mhm.
we use the regularized double shuffle relation, you can write that explicitly.
Ah, okay. So even in those higher depth cases.
But the higher case, we cannot get the explicit.
I see. Okay. Okay, now, and we'll use the explicit form of shuffle and stuffle, but those have been sort of used quite a bit, so I'll drop that part. I think, yeah, I'll do that maybe in the afternoon. And there's a refined sum formula, which I'll also postpone for the afternoon. Okay, so let's ask another question. When are individual Zeta and n's known? And by known I mean rational times power of pi. And so essentially, well, what one can say, if but the arguments are the same, then the Stoffel, which I haven't written, but roughly gives you 1/2 zeta r squared minus zeta 2 times r. So in that sense, you reduce the double zeta also to previously determined zetas, meaning lower depth zetas. But that's not really explicit. But in particular, if you take zeta 2n, zeta 2, comma 2n, that is indeed a rational number times pi to the 4n. So the power of pi is always the weight for all the combinations that are known. And one can be even more precise. One can say, I think it's just 1 over, I'll just give an example. Zeta 6 is 6 times 2 pi to the power 12 divided by 15 factorial. Okay? And there are patterns that you find, but they're not completely obvious, and it's not always obvious how to generalize it. So many of these relations should maybe mention many names of work. Broadhurst and collaborators, Bradley, Borwein, Zagier, I think Hoffman, all these names should appear in the following context, so I'll probably forget to mention them at the right moment, so just let me give you just an impression of the names. And the first weight in which something new happens, at least presumably, where sort of non-Riemann zeta values appear, at least conjecturally, and consistent with all the information that we have on multiple zetas, especially on the motivic side where this is a valid statement, is weight 8. And for instance, zeta 3.5 or zeta 2.6 or 6.2 are conjecturally new, in the sense of that they're not products of Riemann zetas or sums of those. So there's something interesting happens, and this can be also seen in the coproduct that Francis has introduced last time. Okay, so, and we have unexpected further relations for coming from or arising from modular fonts, and this I'll be more precise in this afternoon in session. Okay, so step 3. Maybe I should mention at least a conjectural statement of Broadhurst, who actually encountered those values in physics, rather, in quantum field theory calculations, Feynman graph calculations, and then already in the late 80s, possibly even before the revival by Hoffman and Zagier in the late 80s and early 90s came. And he looked and found that zeta 2a, zeta 2a plus 1, zeta 2b plus 1, so the odd zetas should give you a basis, or at least generates everything, if a is greater or equal to 2b, and this is to 0, generates, or is are the bases, think modular products in in depth 2, and then you can, by the idea that we slice everything into weight graded pieces, and you can say for each weight graded piece, so where a plus b is sort of constant, those will give you a basis in the corresponding slice. And this will come back this afternoon as well. Okay, step 3, just a few words. I should mention names like Marquette, Borwein, Gilgenson, again, Broadhurst, Bradley, Borwein. For even weights, we have, I think that's roughly what we already have discussed. So if a plus b plus c is even, and this is reducible, because depth is of a different parity. So
products of
lower depth. lower depth. So products of double zetas and zetas, and of 3 single zetas as well. And zeta R11 can be expressed explicitly and this is a pattern that keeps on giving. You can add ones only at the end, and this can be expressed explicitly by those people in terms of these products of lower depth. And actually here, in terms of products of Riemann's zeta values. I'll abbreviate RZV, maybe I already did.
So
Riemann zeta values. So
when
single.
you say product, pi square is not a product. It's not product.
It's zeta 2 times zeta 0. Yeah, so if so, like I tried to say up there, so zeta 7 is not really a product as such, but if you write this as minus 11 over minus plus 22 times zeta 7 times zeta 0, then you can sort of subsume it into the same phrase that it's a sum of products. Okay,
If you include zeta 0, right, this is a rational number.
it's a rational number, yes.
All the items, all the bulk becomes
Becomes a product, yes.
But lower depth.
lower.
Lower depth.
Yeah, so low depth. So you work module low depth. Okay, and Broadhurst again gave conjectural basis. If you take 2a plus 1, 2b plus 1, C plus 1 for E greater equal to C and A greater C on basis in depth 3.
So what was your zeta zeros? You're saying you have homogeneous products? What was the zeta zeros comment?
Yeah, one sometimes would like to look at it as a more homogeneous way of writing, but it's unnatural as because it has pointed out. So it's better to say you work modular lower depth, and then that's usually what is done. And it's just too ambiguous having zeta 0 being specified.
Are these conjectures based on computation or
Experiments, lots of experiments, and some of them, I mean, he has done those calculations up to, I think, weight 30 plus. This was quite some substantial work. At the time, maybe, when he made the conjecture, that was maybe over 20 years ago, he had less at his disposal, but now I think there's something nowadays called a model Zeta data mine, which even allows you in principle to use their program that's written in a language it's called form, more for physicists, and by Masseren in Amsterdam, and this was Broadhurst and also Bloemlijn. They sort of put up that data mine, and that's an archive preprint where you can get a lot more impressions on what kind of relations are expected.
Sorry. Today the point is about generating. Do they generate? Since presumably they have
Yes.
the right number of elements.
Well, they already checked that they generate.
But we know the number of elements they should. I mean the dimension.
The upper bound.
Yeah.
But here he says the basis. So
Yeah. So, but it's
So-
about the difficulty about generating of independence.
the big deal is the independence. The generating bit is you test it numerically, whether you find linear relations with small denominators, and if you do, then you discard them, or later on you try to prove them. I think that's what Broadhurst did.
So you start with a number of elements, which is what is predicted by the motivic thing, by this Zagier.
No, you take all of them and successively reduce. So you take a presumable set of generators, and you try to express any other one in terms of those with small linear coefficients and small z coefficients. And if you can, or rational, and if you can do so, then you can discard that, and then you look what's left. So which ones you can't express in terms of each other. And then he came up with that as a good choice of basis, which is not at all obvious how to find. So I think that involved a lot of data mining.
Is it basis or basis up to lower?
Up to yes, in mod lower depth. Products and lower depth, sort of. Yeah, lower depth meaning also products involved. Okay. So arbitrary depth now. So we mix with some conjecture. Is one of the first ones. I think maybe stated by Moen and independently by Hoffman, possibly others. So fix the weight and well, so this doesn't really, well, it sort of mixes, but not in a big way. So on the left side, everything in fixed weight and depth is summed. So everything that's convergent, so such that sum ki equals k, and k1 is greater than 1, just to make it convergent. Then you can sort of distribute z to k like we had for the double zetas. This time you fix the depth and distribute over all possibilities, all these partitions of k into d numbers greater or equal to 1, and the first one should be greater 1. So proved by proved for b equals 3 Moen, and in general by Granville, and independently by Zagier. And there's a duality conjecture also. So this is the large family. Yep.
So this is not a conjecture.
It's a sum. Now it was known as
It's known as
so
that.
former sum conjecture.
I understand.
Yeah.
I understand.
And similarly here, some formula now, or some theorem, or different names. But originally, I think it was called some conjecture. Now,
something like that.
Here is
Solves all problems.
that was some conjecture. Okay. The duality conjecture, also now a former thing, and that was stated originally by Hoffmann, and then independently Zagier found that, and in his famous Paris write-up, he states it without reference to Hoffmann because he just didn't know, so sort of was embarrassed afterwards so that he hadn't seen this before. So I think originally it was due to Hoffmann. And this says, okay, I'll build it up in increasing generality, increasingly general. That is supposed to be logical. So zeta n, why do I say n? I say k. So that's a zeta 2, 1, 1. So where this is the number of k minus 2 ones. So that's the duality in its simplest form. So with a single term here. Now, a bit more general, if you take, say, now let me take n, and number of ones, and suppose this is given by n minus 1 ones, and this is same as zeta n plus 1 with the corresponding number of ones referring to the left argument here. So here's n minus 1 ones here. So you see how n and m interchange roles. Right? So you could say this is equal to itself when you exchange n and m. And the general case is just one more thing you need to understand. They swap the order, so you reflect to np plus 1 and the sequence of ones. Now if we have, say, n1 minus 1 ones, and here np minus 1, and this is zeta of n1 plus 1 and a sequence of ones, which now it's not 1, but it's the other way around. As I said, there's another step involved, np plus 1, and here is np minus 1 up to n1 plus 1 and the sequence marked by n1 minus 1. So that's an increase in increasing complexity. And this was, in a sense, proved. Well, Zagier says that Kantsevich did it. But I think to say maybe that I think they met in a plane, and then Kantsevich mentioned the integral representation for multiple zetas to Zagier, and then Zagier told him, oh, then you've proved the duality conjecture. Sort of an indirect proof. See it? So then there is a kind of co-operatic formula, maybe. You tell me whether that makes any sense, what I'm saying here. Hoffmann's relation. So if you fix indices S1 to SD at 0 with, as usual, first one greater than 1. Did I forget something? I forget?
No, I was asking, but does it have to do with the fact that Greenfeld-Masse Zeta satisfies relation 1 in terms of GRT?
I thought so, but that's sort
Yeah,
of essentially taking the word in zeros and ones, swap it around, and exchange 1 and 0.
Mm-hmm.
So I don't know how that.
It looks maybe, I mean, it could be relation 1 for GRT for the Greenfeld-Masse Zeta, but I don't.
Yeah, you replace x and y.
You
That
replace
means
x and y, so you replace 0 by 1, and it's an involution.
And yeah.
So at least it has some resemblance.
But inverting the series is not just taking the same coefficient, is it? Because here you just check two coefficients, right?
Yeah.
And you check that they are equal.
Yeah.
And the product somehow is more complicated of two Greenfeld, I think. So it feels more complicated.
Yeah.
So then, okay, let me prepare. So the first part, before, say, the rth slot, we put an extra 1 in, and then we have sort of a trailing part, and we subtract the sum over all. Okay, part 1 stays, but then we have one more argument, and we call it, say, t, and we have SR plus 1 minus t, so that the sum of the two successive ones is equal to the previous one. Right? So we sort of spread it out in all possible ways at slot R. That looks sort of rather operatic. And we keep the first part and the second part. Now this is not quite 0, so you can't quite replace the former by the latter, but you can if you sum over all R. So this is 0. That's how it.
There's a comma, so T1, T comma. That's fine, I got it.
So here is
I got it.
SR, let's say the same as here, minus T, comma. Yeah, sorry. Right, so you just spread it out in all possible ways, and I think T has to be greater.
But you lose a slot somewhere.
No.
No? No, you do it for each slot here,
Sorry.
right? R from 1 to D. So here you have in S1 up to SR minus 1, and here you have SR plus 1 to SD. And now you keep those fixed. The rth one you spread out in all possible ways.
So one more slot.
One more slot. So you suddenly raise the depth.
Yeah, okay.
And you do it for all of those and add them up, and you find that's 0. So somehow it's expressing the previous one as a sum of spread out
Why
ones.
do you take R plus 1? I couldn't.
R plus 1.
Yeah,
Because here you have SR.
Yeah.
So here you go up to SR minus 1. Then you have SR. This is the R plus first slot.
But it's, if I call it SR plus 1 T, then, no, I shouldn't call it T, but call it something else. Why do you write as R plus 1? Is the formula downstairs correct? Or is there one missing
Yes.
or something like
No,
this?
no. The sum of these two is the upper
Is
one.
this one, yeah.
You've got some of all the R's, so you can't just change one of them.
No, but why do you call the middle one as R plus 1?
So you fix those, and if you take the sum, then suddenly you take SR minus 1 plus 1. But you have sort of, as your anchor, you have the previous
okay,
one.
you started, okay.
Well, in fact, it looks more like kind of Cobar differential to the second part.
Uh-huh.
You're spreading something.
Okay, so
It's an empty sequence.
question, Cobar differential? Can you make this into a Cobar differential on?
It says something like it is a cycle in Cobar construction.
Uh-huh.
Well, it's some either cheaper way.
Yeah, so since the activity is about bringing those together, maybe any such comment is very welcome. And And so I'll try to formulate, and I hope I did it correctly. I guess you will correct me if I did. Also, the even more, I think, even more general relation by Ono. So, given n 0 and a sequence of indices n dual to a sequence of indices m. So that we have zeta of n, so in particular zeta of n equals zeta of n by the duality formula. Right? So that's a sequence of n's as in the duality formula. Now take zeta n plus q, where q runs over all ordered partition of our fixed number capital N, and ordered absolute value of m partition of n, and that's the same as if you sum over all zeta m plus say underscore p, where p now underscore q here, p underscore runs through all the ordered absolute value of n partitions. So meaning in partitions into those many parts. So partitions of n. Then those are the same. And I think further refinement is due to Ono Hoffman saying in terms of what's called cyclic sum theorem, where you essentially fix the first one and you cycle through the first one. You don't sum like here over all the slots, but you fix the first one and do that operation as before, but only in the first slot. So, not sure. This is roughly.
Which one was that, about Hoffman or Monos?
That's a common refinement, is joined by Hoffman and Ono together, tried, I think, to give an even more general formula, which includes those two. If I understand correctly, they really imply the two, but I'm completely sure. Okay, now okay, just a quick note on double shuffles. So we have MZVs on the one side as a sum over lattice points in a cone. So that's sort of your indexing set, is the lattice points in a cone. And the product of such cones is the union of, in fact, sort of typically it's an open cone, cones of possibly different ranks. So the first example is one that you've certainly seen, is sum m and these are all positive integers. This sum breaks up into m greater n, m smaller n, and sum m equals n. So here is a cone And you can think of, say, this a product of cones, well, in general at least. Here's a very degenerate one. You have one cone, another cone, and sort of diagonal of different rank. Rank 1, rank 2 here. And on the other hand, you can write it as an iterated integral over simplex. And then the product of two simplices in dimensions R, S respectively is a union of R plus S simplices. And that gives rise to so those two decompositions give rise to two types of shuffle. So this is on the left hand side scuffle, and on the right hand side the shuffle. And so these are rather general relations, but they're not quite sufficient. And one sees that already in weight 3. So not sufficient. In a sense, almost, but well, I think we'll hear more about that definitely next week. So zeta of 3 equals zeta 2,1 is not a consequence as such. One needs a notion I already mentioned, regularization. And that will be dealt with next week. And then one conjectures that those give you a complete set of relations.
So,
Okay.
so what you conjecture gives a complete set of relations.
You have
Shuffle,
shuffle,
plus
and the difference between sort of divergent shuffle and divergent shuffle. So if you multiply two zeta MZVs together, you can do it in two ways. You can use the left-hand side, you get a relation coming from the shuffle. You can also do it on the right-hand side, but that you can do sort of even for divergent series, formally. Now, it happens that the divergent ones cancel. If you take the difference of the two, you're left with no divergent term. So you take those as your extra relations. If you do so, you're in business, and that's presumably enough.
And that's all, and that generates all the
That
relations.
presumably generates all the relations.
Could one grade it with your T or something like this? Is there some way of expressing it as
Exactly,
as
yeah.
homogeneous
Yes.
equations which you get graded in T?
Yep. So that will be done in the next week in the regularization business. Exactly. So zeta 1 will sort of function as your extra counter of, say, how divergent a sum is. Okay, so what you may not have seen so much so far, individual evaluations. Again, the same names, Zagi, Broadhurst, collaborators have come up with a bunch of known values. For instance, zeta 2, 2, 2, 2, 2 is known. So if this is, say, n2s, then you have essentially, okay, this is written with a shorthand brace 2 sub n, and this is pi to the 2 times n. So we already know the power of pi by just summing the weights of the individual ones, and divide by 2n plus 1 factorial. So what I mentioned before here, for positive zetas, your remark should be factorials. And more general formula for 2k is known, but okay, that's a bit too complicated to give here. So that was, I think, Japanese mathematician called Nakamura, not Hiroaki, who was here or is here. But I think it was in principle one given by Zaki, but also I think I've seen it in Brothers et al. So that formula has been given several times.
So you mean there is an explicit rational?
As an explicit,
but you're not.
well, you can. It's sort of a recursive thing. You can, in fact, to sum over all partitions of a certain kind. But still, it's a very explicit one.
Yeah,
for every given n, you can just do it. And maybe here I have.
Is generating function of this 2k
Yes.
is a product of the sign?
That's something like that, yes. Or it's was it maybe here it was sine and sinh or something.
Sine x divided by x. Also.
Right. So something like that. And here you have a bit more complicated one, but you're absolutely right.
So what was
So the technique is take the generating function.
X divided by sine, or vice versa.
Sine is on top. Sine is certainly on top. So for those, a good generating function, and you'll learn that next week, is something like maybe t to the 2n. Possibly there was divide by 2n or 2n factorials. I forgot which one was the right. You have to know in advance what the right generating series is, and then it's sort of straightforward. Here it was maybe even without. So that maybe someone knows better than I do.
Is someone going to show us that formula sometime?
Oh yes.
Okay.
No, next week I say.
Oh, okay, sorry.
There will be, as I said, there will be proofs next week, and I'm sure that this one will come up. It's so beautiful and short, and he'll also show that Zeta 3.1. So something I think Francis mentioned that was conjectured by Zagier to be power of 4n divided by maybe 4n plus 2 factorial and maybe a 2 here, some such thing. Yeah, that was. So that was conjectured by Zagier, and a few years later proved by Grothendieck. So this is then so the 3.1 Zeta 3.1 3.1 3.1 is indeed a multiple of a rational multiple of pi to the 4n, and one can even say what that rational number is very explicitly. And then just to give you another such 3, 2, 1, 2 is pi to the 10 over 3 times 11 factorial. Okay, and you can make that. Yeah, actually, maybe I'll state the general conjecture, not completely explicitly, but conjecture by Grothendieck. It sort of makes this more general and incorporates, I think, all of the previous closed formulas. For Zeta question? Wow. So 3, 2m, 1, another 2 sub m, and the whole thing n times. So that's maybe the most general sequence. So you take a sequence of m2s.
Yes.
And then you plug it before a 3,
Yeah, I see.
between 3 and 1, and after. And you do that n times, so apart from the first one. And that gives you a sequence of 2s, 3s, and 1s. And there's always a power of pi. Okay, we can count, right? You have 4m plus 4 times n plus m, plus 2m. So that must be a power of 2. And so this is rational number times that power of pi. Rather generic formula, but so I hope brace. So it just generalizes that. So you take sequences of 2s, and you just take that several times. That's it, right? Once you've done it. It's if you're not used to that form notation, it's a bit.
It's hard to tech.
Okay, so 2. No, left. No. Come on. Okay. Then. Okay.
Can I ask a stupid question?
Yes.
How does he conjecture these things? Does he calculate them, or does he
Yes.
use some graphical language?
No. He has calculated those up to, I don't know how.
By
Up
solving
to,
the sums of the integrals or whatever.
No. The way out. That's another thing that probably comes up next week. How to compute these zeta values,
Yes.
and so Zagir will tell you how to do that efficiently. Brot has had different approach, but they're maybe similarly efficient. And then he went up to well, once you guess your formula, it's a very simple thing. You just compute that number and up to say 100 decimal digits, divide by the corresponding power of pi and the factorials that you expect, and then the remaining rational will be very small, so it's easy to detect. And I think that's must be the way that he used that. And there are wonderful programs, PSLQ and LINDEP in different languages, which give you linear dependence between real numbers, and that helps a lot in experiments.
Is this rational number explicitly conjectural?
Yes, so he gives a closed formula, explicit formula for this.
But it's not some counting item, because it sounded like when you were saying you're counting partitions that you were counting some sort of combinatorial gadgets.
Yeah, in a sense. And I mean, using Francis's language, for instance, with the derivations,
Yes.
that is certainly a way that you can approach it. And I hope I hear from someone who I've given that as a task, who's here in the audience. So you tell me that this one is easily deduced from Francis's formula, right? And if you take multiple chains of those here, so if you take the periodic thing, did you also find cancellation for those?
The explicit examples, they do seem to cancel.
Okay, so there seems to be a good way to say from the start, by combinatorial gadget, that this has to be a rational multiple of corresponding power of pi, like what Francis told us. If you have that all the derivations, odd derivations that he called d sub 3, d sub 5 and so on, if they go to 0, that's enough to say that this is a rational multiple times zeta, a power of zeta 2. So therefore that's where the combinatorial game comes in. It seems a rather powerful one. Yeah, okay, I have finally one of my own conjecture. So there's something like refined some formulas, the history of which I'm not completely sure of. So there's a weighted sum formula. So if you take zeta r and k minus r for a fixed k, and you let r run as before from 2 to k minus 1, we know that this is equal to zeta of k. Right? But now you can plug in here, I think power 2 to the R, and you still get a multiple of zeta k. I think k plus 1 maybe, what I seem to see. So it's referred to as Ono and Zudilin, but I think Ono told me that you had some such formula. Is that correct?
I forgot.
You forgot? Ah, okay. So, well, if you forget, then or maybe I misremember that he mentioned some name, and I thought it was yours. So it's some such weighted formula, and there is a generalization, but much less pretty, to high depth. It's always a kind of distribution of zeta k into all partitions of a certain kind. And so my own conjecture, and I would like to present in depth 3, is that the sum of the odds, so if you only plug in odd arguments and take all the convergent ones, and of course the sum of these equal to a fixed weight k, this is sort of reducible. It lies in products. And actually, I think that may answer the question, because zeta k can be written as a sum of products itself, so you can either forget about it or not, right? There is a sum formula, so instead of writing zeta 7 as I did up there, I could have just written the combination of zeta 7 as products, and then it would be a bit more, say, homogeneous in the way to write it.
What are you summing over there?
The sum over all convergent expressions, zeta odd, with the same weight. Right? It's always that, maybe that should be some upper C to mark this. And that's, I think, not completely obvious, and more precisely, if we let L and M be odd, and zeta L M k minus those two, this is the sum of Cn zeta 2n plus 1 zeta k minus 2n plus 1 plus another coefficient for zeta k, and here the sum runs from 1 to k minus 3 over 2, where the Cn is the coefficient in the following rational expression. Divide by 2 times x minus 1 squared times 1 minus 4x, and take sort of the nth coefficient, meaning the coefficient of t to the n in the expansion of that as a power series. And similarly, dn is given by a different one with a similar denominator. So minus x times 2x squared plus 9x plus 1, divide by 8 times x minus 1 cubed times 1 minus 4x. Cool. So all I want to say, an explicit formula for the sum of the odd triple zetas in fixed weight, and the coefficients are rather complicated but still sort of regular in that sense. And so I don't think this is proved anywhere.
Plus one is take the nth coefficient.
Take the nth coefficient, thank you. Yes, exactly. Right, so bracket f sub n, coefficient of t to the n, say f of t, in power series for f of t. Just a standard convention, like I think Zaghi uses that a standard convention as well. So yeah, I didn't get around to say anything about dimensions, but I think you've already seen sort of the dimension formula, and maybe and Hoffman's basis. I've glossed over many other developments. So I've got a whole list, which I could, let me at least refer to next week's talk about derivations. So there will be relations coming from derivations on multiple zetas. That will be Kentaro's talk next week on Tuesday. There's a third set of relations which hasn't been looked at so much. Kawashima, a young Japanese mathematician who may now have left the field, has come up, and I think Tanaka, a student of Kaneko's, says together, so Kawashima's relations together with the ones coming from derivations, that may be also a complete set of relations. So that's the third one, as opposed to associator relations being everything, double shuffle, or extended double shuffle being everything, possibly. Maybe you know more about Kawashima's relations, or have you seen Kawashima's relations using like Fourier type of inversion or sort of discrete Fourier inversion or in transformations? Another thing I didn't mention was alternating sums called Euler-Zagier sums. So we have the multiple zetas, but possibly with powers, with signs and their powers. Zeta stars, meaning if you take, instead of the sum itself, you can, instead of summing m greater n, you can also take sum m greater equal to n, and that goes from zetas to, like Ono, for instance, and Zudilin, called zeta stars. Connection to physics, I didn't mention, periods, associated, okay, negative zetas. Well, so all I wanted to give is a kind of panopticon of results, and I hope you've got an idea of what kind of relations there are still out, apart from the double shuffle that had been the name of the game most of the last weeks. So, thank you.
But I've asked a question already. So. No, I mean, no, it's just that this is only in the real world, which is very good.
Mm-hmm.
But is it easy now to determine whether any such relation is motivic or not?
Well, Francis has given a kind of,
a kind of recipe
how to lift
so
in certain situations.
Probably in all the relations you've presented, I mean, they are motivic, but nobody has really taken the trouble yet to say this is a...
Yeah, I think in each case it's not completely obvious how to prove. For instance, in Tomohide's talk, he gave sort of, that was different. He lifted it to the associator stage. But you're just asking what... okay, so you're asking motivic, yeah.
I mean, you take any relation like this and you ask yourself, can I put a little m? So this is doable, but difficult.
I'm not sure about the doable in general. I think only for a certain type of formula you might expect it to be straightforward. I mean, we expect everything to come from those. I think in that sense it should, but
using motivic means you are expecting geometric interpretation.
No, just what false. I mean, with the definition of the motivic multiple zeta values, do you have the same relation?
Well, this afternoon I'll talk about the double zetas and what sort of follows on the formal side, and then sort of also show a difference between the formal side and sort of the actual real side, and there will be a difference, and that comes from modular forms by some strange reason. So maybe that's more in this direction, where what's the difference between the formal side and the realization in the real numbers. Maybe that answers some. Okay, so yeah, maybe.